Welcome to Cloud Wizard. In this video, we're doing a complete deep dive into the data pipeline and ETL system, the engine that ingests, cleans, transforms, and serves data at scale for analytics and machine learning. We'll cover how modern platforms use Kafka, Airflow, Spark, data lakes, and schema registries to move billions of events per day. Whether you're preparing for a senior engineering interview or building data infrastructure, this one is for you. Let's get into it. Welcome to Cloud Wizard. In this video, we're doing a complete deep dive into the data pipeline and ETL system, the engine that moves, transforms, and prepares data for analytics, machine learning, and business decisions. If you have ever wondered how companies like Netflix, Uber, or Airbnb ingest billions of events per day, clean them, join them, and load them into data warehouses and data lakes, this video is for you. We'll walk through the functional requirements, non-functional requirements, system architecture, end-to-end user journey, core models, low-level design, and the trade-offs that come up in a senior system design interview. Whether you are preparing for a FANG interview or building data infrastructure, let's get into it. Here is the core problem. A data-driven company has hundreds of data sources: application logs, clickstream events, transactional databases, third-party APIs, mobile SDKs, and IoT sensors. Every team needs data. Product analysts need dashboards, data scientists need training datasets, finance needs revenue reports, and operations needs alerts. The data arrives in different formats, schemas, and velocities. Some records are missing fields, some contain duplicates, some are delayed by hours, and some are outright wrong. Without a reliable data pipeline and ETL system, teams spend 80% of their time cleaning data instead of using it, and critical business decisions are made on stale or incorrect information. The business needs a scalable, observable, and resilient pipeline that can ingest, transform, validate, and load data in near real time. Let's walk through the functional requirements. First, the pipeline must ingest data from many sources, including event streams, relational databases, object storage, APIs, and message queues, with support for both batch and streaming modes. Second, it must support transformation logic, from simple filtering and mapping to complex joins, aggregations, windowing, and enrichment. Third, it must provide data quality and validation, including schema checks, null checks, duplicate detection, anomaly detection, and lineage tracking. Fourth, it must orchestrate and schedule workflows, with dependencies, retries, backfills, and monitoring. Fifth, it must load data into multiple destinations such as data warehouses, data lakes, and search indexes, with support for incremental loads and partitioning. These 5 capabilities make the pipeline a production-grade data platform. Now the non-functional requirements. The pipeline must be scalable, handling anywhere from thousands to billions of events per day with horizontal scaling of compute and storage. It must be reliable, with exactly once or at least once semantics, checkpointing, and failure recovery. Latency matters. Some workloads need minutes, while others can tolerate hours. It must be observable with metrics, logs, and lineage for every job and every dataset. It must be flexible enough to support evolving schemas and new data sources without stopping the pipeline. Security is critical with encryption, access control, and masking of sensitive fields. And finally, it must be cost-efficient, because data pipelines can consume massive compute and storage resources. Here is the high-level system architecture. On the left, data sources push or pull data into the ingestion layer. Message queues like Kafka, change data capture from databases, object storage uploads, and API connectors. A streaming ingestion layer buffers raw data and decouples producers from consumers. Stream processors clean, validate, and enrich events in real time, writing results to a raw data lake or a hot serving store. A batch processing engine such as Spark runs scheduled ETL jobs that perform large-scale joins, aggregations, and historical recomputation. An orchestrator like Airflow schedules jobs, manages dependencies, and handles retries. A metadata and schema registry tracks dataset schemas, lineage, and data quality rules. A data warehouse serves curated data for analytics and reporting. A monitoring and alerting layer tracks job health, latency, and data quality issues. The key metrics to memorize cold. Pipeline latency, the time from data creation to availability in the destination. Throughput, events or bytes processed per second. Data freshness, how recently the destination was updated. Data quality score, the percentage of records passing validation checks. Job success rate, the fraction of pipeline runs that complete without failure. Cost per million events processed, which helps optimize infrastructure. Schema compatibility, the percentage of incoming data that conforms to the registered schema. And replay and backfill time, how long it takes to reprocess a day of historical data. These metrics are what data platform teams actually care about. Let's trace the end-to-end user journey. A data analyst at a retail company needs to build a daily revenue dashboard. She submits a new data source request through a self-service portal, a Postgres database containing orders. The platform team configures a change data capture connector that streams changes to Kafka. A streaming job validates and normalizes the events, writing them into a raw zone in the data lake. An Airflow DAG runs every hour, joining the raw order events with customer and product reference data, and writes the curated output to a data warehouse. The analyst queries the warehouse in her dashboard tool. When the data quality monitor flags a sudden drop in order events, the pipeline team gets an alert, checks the lineage graph, identifies a broken upstream API, and reruns the affected partition. The dashboard is back to accurate within the SLA. The core models and algorithms. The ingestion model defines how each source connects, the frequency of data capture, and the delivery semantics. The transformation graph is a DAG of operations such as filter, map, join, aggregate, and window. The schema registry stores canonical schemas and enforces backward and forward compatibility. Data quality rules define validation checks and how to handle failures, such as quarantine or alert. Lineage tracks the flow from source to destination at the dataset, job, and column level. The partitioning model decides how data is organized by time, region, or tenant for efficient querying and backfills. The key trade-off is between strict schema enforcement, which catches errors early but breaks fragile sources, and flexible ingestion, which accepts messy data but pushes quality problems downstream. Now the low-level design deep dive. The ingestion layer uses connectors to pull data into a durable message bus, with each source assigned to a topic and partition key to preserve ordering where needed. A stream processor consumes events, applies a transformation DAG, and writes results to a raw or curated layer. The orchestrator stores job definitions, schedules, dependencies, and state in a metadata database. Each ETL job runs as a containerized task and emits heartbeats, logs, and metrics. The data catalog maps physical tables to logical datasets, tracks owners, and exposes lineage. The data quality engine runs rule checks inline or after load, storing results in a quality store. Backfills are handled by reprocessing specific partitions, using idempotent writes to avoid duplicates. The API layer exposes endpoints for job status, lineage, and data discovery. Key takeaways for your interview. First, a data pipeline is not just extract, transform, load. It is a distributed system with ingestion, stream processing, batch processing, orchestration, lineage, and quality. Second, always separate the raw, curated, and serving layers of a data lake or medallion architecture. Third, expect questions about delivery semantics. At least once, exactly once, and ordering guarantees and when to use each. Fourth, schema evolution and data quality are first-class design problems, not afterthoughts. Fifth, observability and lineage are critical for debugging data issues, and they are often the difference between a pipeline that works and one that silently corrupts reports. If you can walk through this system with these 5 points, you will signal strong senior-level design thinking. That's it for the data pipeline and ETL system. If this helped, like and subscribe, and I'll see you in the next one at Cloud Wizard. And that's a wrap on the data pipeline and ETL system. We covered the full picture from ingestion and stream processing through batch ETL, orchestration, data quality, lineage, and the low-level design of the pipeline DAG. If this video helped you, Please hit that subscribe button and the bell icon so you never miss a new system design video. Drop your questions in the comments below. I read every single one. See you in the next one at Cloud Wizard.